Hello students, welcome to all. In last lecture, we discussed about having distance and its properties. Now today we are going to study a group code. So here we start the definition of group code. So definition, a group code. Definition and MN encoding function E from B raised to M to B raised to N, and MN encoding function E from B raised to M to B raised to N is called a group code if E of B raised to M equals to E of B as B belongs to B raised to M, and which is equals to range of E is a subgroup of B raised to N. So see here definition of group code and MN encoding function E from B raised to M to B raised to N. It's called a group code if E of B raised to M is equals to E of B as B belongs to B raised to M, and this set is nothing but the range of E is a subgroup of B raised to N. Okay, so if E of B raised to M is subgroup of B raised to N, then we say that the given encoding function is a group code. Now see here, we know the concept of group and subgroup. So here we already know that a non-empty subset H of group G is a subgroup if it satisfies the closure property, and second one, every element has inverse in H. Then we say that H is a subgroup of group G. Okay. Now see here, we all know that every element of B raised to N is inverse of itself. Every element of B raised to N is inverse of itself, right? And here, so to show that the given encoding function is group code, so here we want to only show that there exists an identity element and it satisfies the closure property. If the encoding function satisfies these two properties, then we say that it is a group code. Remember, for group code, here we want to prove only two properties. First, there exists identity element, and second, this encoding function satisfy the closure property, that is x ring sum y belongs to B raised to M. Okay, now we take the example. Show that the 2,5 encoding function E from B square to B raised to 5 defined as E of 0 0 equals to 0 0 0 0 0, E of 0 1 equals to 0 1 1 1 0, E of 1 0 equals to 1 0 1 0 1, and E of 1 1 equals to 1 1 0 1 1 is a group code. group code. So here we want to show that this encoding function 25 is a group code. So now here we see the definition of group code. So by using this definition, that means here we already know that in b raised to n, every element is inverse of itself. Okay, so here to show that this is a group code, it is enough to show that there exists an identity element belongs to E of b raised to m and it satisfies the closure property. Okay, so we start the solution. Here E of 0 0 equals to 0 0 0 0 0 is an identity element belongs to E of b raised to 2, right? So this identity element belongs to E of b square, that is there exists an identity element. Now we write operation table to ensure that for every xy belongs to E of b square, to ensure that every xy belongs to E of b square, x ring sum y also belongs to E of b square, right? So here we construct operation table for ring sum. We write operation table to ensure that for every xy belongs to E of b square, x ring sum y also belongs to E of b square. So here we write the operation table for operation ring sum. So here operation table for ring sum 0 0 0, then 0 1 1 1 0, then 1 0 1 0 1, and last one 1 1 0 1 1. Now here 0 0 0 0 0, 0 1 1 1 0, now 1 0 1 0 1, and here 1 1 0 1 1. So now see here operation is ring sum. So identity element, ring sum, any element, then we get that element itself. So we write here 0 0 0 0 0, 0 1 1 1 0, 1 0 1 0 1, 1 1 0 1 1. And here again same identity element, ring sum, that element itself. Okay, so here we get 0 1 1 1 0, 1 0 1 0 1, and 1 1 0 1 1. Now next one 0 plus 0, 1 plus 1, again 1 plus 1, 1 plus 1, and 0. So here we get the identity element. Now next 1 plus 0 is 1, 0 plus 1, 1 plus 1, 0 plus 1, and 1 plus 0. Now next 0 plus 1, then 1 plus 1 0, ring sum 0 ring sum 1 is 1, 1 1, and last 1 0. Similarly, so this is operation table for ring sum. Now observe this table. Suppose we consider this 0 1 1 1 0, ring sum 1 0 1 0 1. then we get 11011, which again belongs to E of B square. So in this way we check whether this every element belongs to E of B square or not. So here we observe the table and every element belongs to E of B square. So from operation table for ring sum for every xy belongs to E of B square, x ring sum y belongs to E of B square, right? So therefore E of B square is a subgroup of B raised to 5. So therefore E is a group. Okay, so here E of B square is a subgroup of B raised to 5 and hence E is a group code. So all of you get it this example how to show the given encoding function is group code or not. So for showing that it is group code, here we want to only prove that it satisfies the identity property, that is there exists identity element, and it satisfies the closure property, that is for every x and y belongs to E of B raised to m, x ring sum y also belongs to E of B raised to m. Then we get it is a subgroup of B raised to n, and after getting it is subgroup E of B raised to m is a subgroup of B raised to n, then we say that E is a group code. Now we take the next theorem depend on this concept group code. So we take theorem. Statement: let E from B raised to m to B raised to n be a group code the minimum distance of E is the minimum weight of a non-zero code word. So see here statement: E from B raised to m to B raised to n be a group code. The minimum distance of E is the minimum weight of non-zero code word. Okay, now we see the proof. Let delta be the minimum distance of E. Delta be the minimum distance of E. Let x and y belongs to B raised to m. X and y belongs to B raised to m such that delta of xy is equals to delta. Let delta be the minimum distance of an encoding function E, xy belongs to B raised to m such that delta of xy is equals to delta. Now here we take let w be the minimum weight of a non-zero code word, of a non-zero code word. So we take W equals to mod Z for some Z. Okay, now here, now we compute X ring sum Y. It is a non-zero code word. Okay, now see here, delta equals to delta of xy, and delta is nothing but the minimum distance, and delta of xy is nothing but weight of x ring sum y. So here weight of x ring sum y, and here w be the minimum weight. Okay, so that means weight of x ring sum y is either greater than or equals to w, since w is a minimum weight. See here, delta is a minimum distance and delta is equals to delta of xy, and we know that delta of xy is the weight of x ring sum y. So this weight is either greater than or equals to the minimum weight w. Now we give it to the number first. Now here second part, on the other hand, W is equals to mod Z, and mod Z, that is weight of Z, and weight of Z, that is Z ring sum 0, and Z ring sum 0, that is distance between Z and 0, right? Distance between Z and 0, which is either greater than or equals to minimum distance delta. Minimum weight W is equals to weight of Z. So weight of Z is nothing but Z ring sum 0. So weight of Z ring sum 0, that is delta of Z0. So here delta is minimum distance. So this minimum distance between Z and 0 is either greater than or equals to the minimum distance of encoding function E. So we give it to the number second. So see here, first, from first, delta is greater than or equals to W, and here in second, W is greater than or equals to delta. So from 1 and 2, we get delta equals to W, that is minimum distance of E is the minimum weight of a non-zero code word, that is minimum distance of E is the minimum weight of a non-zero code word. So all of you get it, the proof of this theorem, minimum distance of an encoding function E is the minimum weight of a non-zero code word. Okay, so here we use this theorem, we use the statement of this theorem to solve the problem. Okay, so we take a problem depend on this theorem. Example, define E b square to b raised to 5 encoding function as E of 0 0 equals to 0 0 0 0 0, E of 0 1 equals to 0 1 1 1 0, E of 1 0 equals to 1 0 1 0 1 and E of 1 1 equals to 1 1 0 1 1. Find minimum distance of E, right? So see here, we want to find the minimum distance of function E. So here we take solution by the definition of a minimum distance we required to find 6 distances, out of which we choose a minimum as a minimum distance, as a minimum distance. So by the definition of a minimum distance, we require to find the 6 distances. Here total code word 4, right? We consider the pair of 2 words. So 4C2 is nothing but 6. So here we want to find 6 distances and out of which we choose a minimum as a minimum distance. So to avoid these calculations, we apply the theorem here. To avoid these calculations, we apply the previous theorem here. We apply the previous theorem. So here the theorem states that, or we know that the minimum distance of E is the minimum weight of non-zero code word, right? So here we find weight, here we find the minimum weight of a non-zero code word. So here non-zero code words are 3, E of 0 1, E of 1 0 and E of 1 1. So we find the weight of these 3 code words. So first E of 0 1. So weight of E of 0 1, weight that is number of 1. So here number of ones are 3. So weight of 0 1 is 3. Now weight of 1 0, E of 1 0. So here again it contains 3 1. So weight is 3. And next E of 1 1. Weight of E of 1 1 is 4. Right? Now here among these weights we want to find the minimum weight. So here minimum weight is 3. Right? Here minimum weight is, so here the minimum weight is 3, hence minimum distance of E is 3. Okay, all of you get it this problem, how to apply the theorem here. So the minimum distance of E is the minimum weight of a non-zero code word. Okay, all of you get it this. So today we stop here. Thank you.